Hey everyone, आज के इस एक्सप्लेनर में हम फोर्स चैप्टर को perfectly decode करेंगे. If you're an ICSE Class 10 student looking to actually master this chapter, well, you're in the exact right place. Consider this your ultimate zero to hero exam review guide. We're going to break down every single concept, every formula, and those tricky board questions into super clear takeaways. By the end of this, you'll be walking into that exam room with absolute confidence. So let's get into it.
Okay, here's our game plan for today. First, force our turning effect. Second, the torque our couple concept. Third up is equilibrium, both static and dynamic. And finally, we'll wrap up with some center of gravity tricks.
All right, starting right off with Section 1, Force our Turning Effect, the absolute basics.
Now you already know the basics, right? A force is a push or a pull. It starts motion, stops it, or changes direction. But before we get into the heavy turning mechanics, there is a guaranteed 1-mark board question we need to just knock out right now. Board exam में ये ज़रूर आएगा, for sure. You absolutely have to know the relationship between the SI unit of force, the Newton, and the CGS unit, the dyne. 1 Newton is permanently equal to 10 to the power of 5 dyne. Seriously, just lock that number in your head right now. 10 to the power of 5. It's an easy mark you really don't want to miss.
Okay, so let's split motion into two completely different categories. On one side, we've got linear or translational motion. That happens when you just apply a straight force, like pushing a heavy box across the floor. But on the other side, we have rotational motion. Think about turning a steering wheel. You aren't just pushing it straight, you're actually making it spin. And to do that, a simple straight force just doesn't cut it. You specifically need a turning effect, which brings us perfectly to our next big concept.
Section 2, Torque or Couple Concept. Let's decode the math behind the turning effect.
So here's the absolute crucial point. Torque, or the moment of force, isn't just about how hard you push. It's actually calculated as the force multiplied by the perpendicular distance from the pivot point. Think about it. If you apply a massive amount of force, but you push right exactly at the hinge, the distance is 0, right? So the object literally won't turn. The perpendicular distance from the pivot is the real game changer here.
All right, time for a really quick concept test, just to keep those gears turning. When you calculate torque, direction actually matters, because it's a vector quantity. So, tell me, is a clockwise moment considered positive or negative? Just think about it for a second.
ध्यान से सुनना, because this is such a common mistake on exams. A clockwise turning effect is always taken as negative, and an anti-clockwise turn is positive. But why? Well, it all comes down to the right-hand rule. If you curl your fingers in a clockwise turn, your thumb points inward, right, away from you, that's negative. But if you turn anti-clockwise, your thumb points outward, right towards you, and that is positive. Make sure you keep this sign convention locked in for your numericals.
Let's actually tie this formula to a real-world application you see on exams all the time. Opening a door. To open a specific heavy door, the minimum torque required is a fixed mathematical value. It doesn't change. Now, since torque equals force times distance, if you put the handle all the way out at the edge of the door, you are maximizing that perpendicular distance from the hinge. And because the distance is maximized, the actual physical force you have to apply is minimized. I mean, that's exactly why you literally never see a door handle placed right in the middle of a door.
And this brilliantly illustrates the couple concept. What happens when you turn on a tap, or turn that steering wheel we talked about earlier? You aren't just applying one single force. You're actually applying two equal, opposite, and parallel forces that don't act on the same line. This creates pure rotational motion without pushing the whole thing forward. The moment of a couple is just that force multiplied by the total perpendicular distance between the two forces. Pretty elegant, right?
Moving on to Section 3, equilibrium, both static and dynamic. Okay, there's a massive misconception here that equilibrium just means an object is completely stopped. Definitely not true. Equilibrium simply means the net force is 0 and the net torque is perfectly 0. So we actually have two types. Static equilibrium is probably what you're thinking of, a body entirely at rest, like a heavy book just sitting on a desk. But dynamic equilibrium, that means the body is in constant, uniform motion. Imagine a raindrop falling in a constant terminal velocity, or a satellite orbiting the Earth at a steady speed. The net force is 0, meaning 0 acceleration, but it is definitely still moving.
अब इस trick को समझो. When you get a numerical board question about, say, balancing a seesaw or a meter rule, you need to use the principle of moments. And here is your fail-proof step-by-step procedure to crush it. Step 1. Identify your exact pivot point. Step 2.
calculate the total clockwise moments using force times distance. Step 3, calculate the total anti-clockwise moments. And step 4, because the system is in equilibrium, just equate them. The net torque is 0, so clockwise equals anti-clockwise. Stick to these 4 steps and you'll nail any numerical they throw at you.
Finally, Section 4, Center of Gravity Tricks.
Now this is probably the most visually tricky, memorization-heavy part of the entire chapter, so stick with me here. First, the definition. The center of gravity, or CG, is that specific point where the entire weight of the body is assumed to be concentrated. But here's the secret. It doesn't strictly have to be in the dead center geometrically. The CG naturally gravitates and shifts towards wherever the mass is distributed the thickest.
Honestly, I highly recommend taking a screenshot of this ultimate CG cheat sheet right now. These exact fractions show up as high-yield questions all the time. For uniform, symmetrical stuff like a solid cylinder or a ring, it's right in the geometric center. Super easy. But for a semicircular disk, it's 4r over 3 pi from the diameter. A solid cone is at height h over 4 from the base, while a hollow cone is at h over 3.
Let's look a bit closer at why this actually happens, specifically with the cone. Why the difference? Well, in a solid cone, the whole thing is packed with material, which means that wider base is super heavy, pulling the CG lower, down to h4. But in a hollow cone, think of a birthday party hat, you've essentially scooped out all that heavy solid stuff from the inside. Since there's relatively less weight at the bottom now, the center of gravity naturally shifts slightly upwards to h3. It's all about where that mass is sitting.
Next up is a classic board exam logic puzzle, the free suspension trick. If the exam gives you a weird, totally irregular shape, like a bent kite or something, and asks where the CG is, just remember this rule. If you hang any object freely from a string, gravity just takes over. The object will swing and rotate until the center of gravity comes to rest exactly, perfectly vertically below the point of suspension. That's the only possible way the net torque becomes 0.
And that brings us to our final brain-teasing cliffhanger for this explainer. अगर एक solid bowl, meaning a hollow hemisphere, में तेल यानी oil भर दिया जाए, तो center of gravity ऊपर shift होगा या नीचे? Think about it. If you pour heavy oil into an empty bowl, the mass distribution is suddenly way heavier towards the top layer of that liquid compared to the empty curved bottom. So where does that pull the balance point? I'm going to let you chew on that one. Test your newly sharpened physics instincts and figure it out. Thanks so much for joining this exam review guide. Keep studying hard and good luck mastering physics.